Hey there. In this video, we're going to talk about empirical and molecular formulas. An empirical formula is the whole number ratio of all the atoms in a molecule. Whole number ratio of the atoms in a molecule. On the other hand, a molecular formula is the actual number of atoms in a molecule. So let's do a quick example to talk about that. Hydrogen peroxide has the formula H2O2. If I was asked to find the empirical formula for hydrogen peroxide, I need to take a common ratio between the hydrogens and the oxygens. So what I can do is I can divide both of these by 2, and I would get a nice ratio of HO. So that would be my empirical formula, HO, right here. Now, if I was asked to find the empirical formula, and you were already given ahead of time that hydrogen peroxide's formula is H2O2, then this would be the actual empirical formula, H2O2. Because in the hydrogen peroxide molecule, there are exactly 2 hydrogen atoms and 2 oxygen atoms. So now let's talk about a sample problem that you'll often get when you're dealing with empirical and molecular formulas. So here's the question. Cuproic acid has the odor of goats. The compound contains only carbon, hydrogen, and oxygen, and was experimentally found to have the molar mass of 110 plus or minus 10 grams per mole. When a 1 gram sample of cuproic acid is burned in excess oxygen, 2.275 grams of carbon dioxide and 0.929 grams of H2O are collected. Determine the empirical formula and molecular formula of cuproic acid. Okay, so whenever you have these types of problems, the first step that you should always take is to figure out the empirical formula. And then from there, you can use the empirical formula to get the molecular formula. And once we do this problem, you'll see why I take these exact steps. So first, in order to find the molecular formula, remember that empirical formula. Remember that the empirical formula is always a whole number ratio of the moles of each element inside a molecule. So in this case, we want to figure out the moles of carbon, the moles of hydrogen, and the moles of oxygen, because we're told that these 3 elements only make up cuproic acid. So how do we get moles of carbon, and how do we get moles of hydrogen, and then how do we get moles of oxygen? So lucky for us, we're given the grams of carbon dioxide and the grams of H2O in this example. So what we can do is we can first find grams of carbon, and then we can find grams of hydrogen, and then using those 2, we can finally get grams of oxygen. Then we can convert from grams into moles, and then we can use the moles to figure out the simplest whole number ratio. So let's go ahead and let's start with the 2.275 grams of carbon dioxide. 2.275 grams carbon dioxide. Let's draw a line here to differentiate it. Okay. So we want to go from 2.275 grams of carbon dioxide all the way to grams of carbon. And that's the big kahuna. We want to figure out how do we get from here. So first, what we can do is we can go from grams of carbon dioxide into moles of carbon dioxide. So 1 mole carbon dioxide is approximately 44 grams. Then we go from mole of carbon dioxide to a mole of carbon, because there's 1 mole of carbon in 1 mole of carbon dioxide. Then from there, we go from moles of carbon into grams of carbon. So 1 mole of carbon is approximately 12 grams. Nice. Now we can go through and multiply all our numbers. So I'm going to do 2.275 times 12, and then we divide that by 44, and what we get is 0.6205 grams of carbon. So now that we've gotten grams of carbon, let's get grams of hydrogen next. So we're told that there's 0.929 grams of H2O. So let me write that down. 0.929 grams H2O. And remember, the goal for us is to get grams of hydrogen at the end of this dimensional analysis. So let's go through and do that. Oops, that looks like a 6. That is meant to be multiplication. So we multiply this by 1 mole of H2O has 18 grams inside of it. We want to go from grams of H2O into moles of H2O. And then from there, we go from moles of H2O into moles of H. So 1 mole of H2O has 2 moles of H, because right here it's H2, so that's why there are 2 moles of hydrogen. Great. So now we can go from moles of hydrogen into grams of hydrogen. So 1 mole of hydrogen has 1 gram of it inside. So now let's go through and multiply everything. So we had 0.929 times 2 times 1, and then we divide that by 18, and that gives us 0.103 grams of H. So now I'm going to write down all the values that we got right here and right here. So we know that there are 0.6205 grams of carbon plus 0.103 grams of hydrogen. And now what we need to do is get grams of oxygen. And we're told that all these numbers that we calculated, the grams of carbon dioxide and the grams of H2O, these numbers were found when a 1 gram sample of caproic acid was burnt. And we also know that caproic acid can only have carbon, hydrogen, and oxygen. So if we've already gotten the amount of carbon, hydrogen, then we can use that 1 gram to get us the amount of oxygen. And so if we add all of these together, that should get us the 1 gram of caproic acid. So now we can treat this exactly like a algebra problem. We'll just set this to x. And now, in order to solve for x, you subtract, you do 1 minus 0.103 minus 0.6205. And that gets you exactly 0.2765 grams of oxygen. So now we've gotten grams of oxygen, and we've also gotten grams of hydrogen and grams of carbon. So now I'm going to write this out right here so that we have all our values right next to each other. So we have 0.265 grams of oxygen. Now we need to convert all of these values into moles of oxygen, moles of hydrogen, and moles of carbon. So let's go ahead and do that. So we go from grams of oxygen into 1 mole of oxygen, which has 16 grams inside of it. Now we can multiply this value, and what we will get is 0.0172815 moles of oxygen. Let's erase this, make it a different color, oxygen. And then we can go from grams of hydrogen into moles of hydrogen. So we multiply all these values. So 1 mole hydrogen has 1 gram of hydrogen. Lucky for us, that's just 1 times 0.103. So that just leaves us with exactly 0.103 grams, not grams, moles of hydrogen. And now we also have to convert from grams of carbon to moles of carbon. So 1 mole of carbon is 12 grams of carbon. And so that equals 0.6205 divided by 12, 0.0517 mole carbon. Okay, so now we have these values, and it's pretty tempting to just say that, oh, we're done right here. We can just write our formula as oxygen 0.0172815, hydrogen 0.103, and finally carbon 0.0517. But this looks ridiculous. It doesn't make sense to have decimal places inside our molecular formulas. So that's why when I mentioned up here earlier that the empirical formula is always a whole number ratio. So here we need to convert these decimal values all into whole numbers, into a ratio between all of these. The simplest way that you can do all this is by dividing each number by the lowest value out of these three. And so here the lowest value is 0.0172815. So go through and we'll divide all these. So we get 0.0172815. Divide this one by 0.0172815. And then finally divide this by 0.0172815. And now that gets you oxygen is 1, hydrogen is approximately 6, and carbon is approximately 3. Now that we've gotten the empirical formula, let's try and figure out the molecular formula. So what we need to do to go from empirical to molecular is we need to compare the molar masses of the actual caproic acid molecule and our empirical formula. First, let's figure out the molar mass of our empirical formula. We see that the molar mass is, if we take OH6C3 and we add all the molar masses of each atom, we get 16 plus 1 times 6 plus 12 times 3, which gets us exactly 58 grams. So now let's see what the actual molar mass of our molecular formula is. So if we look at the second sentence, it tells us that the molar mass is 110 plus or minus 10 grams per mole. So this means that our molar mass can fall within 100 grams per mole to 120 grams per mole. So now what we can do is if we multiply this whole molecule by 2, so we do 2 times OH6C3, we're going to get that this formula would be O2H12C6. And the molar mass of this thing is 58 times 2, which is 116 grams. And what we can see is that this falls within our range of 100 to 120 grams per mole. And so this right here is our empirical formula. So that wraps up this video. Thanks for watching, and I'll see you in the next one.